Welcome to this video on Quantum Physics Unmasked, where we will explore radiation, photons, and matter waves. We'll trace the quantum revolution from the crisis of classical physics to the wave nature of matter. At the turn of the 20th century, classical physics faced a catastrophic failure, the ultraviolet catastrophe. Classical theory predicted that black bodies should emit infinite energy at short wavelengths, directly contradicting experiments showing a finite peak. This fundamental crack in classical physics demanded an entirely new framework. Experimental observations of blackbody radiation were key. The spectrum shape depends only on temperature and features a distinct peak. Higher temperatures shift the peak to shorter wavelengths, and total emitted power increases with the fourth power of temperature. These reproducible features could not be explained by classical theory. In 1900, Max Planck introduced a radical assumption. Energy is exchanged in discrete packets, or quanta, defined by E equals nh nu. This quantum hypothesis led to Planck's radiation law, which perfectly matched the experimental blackbody curve at all wavelengths. Planck's constant, h, emerged as a new fundamental constant of nature. Planck's quantization explained the high-frequency suppression. Since energy is not continuous, the thermal energy available at high frequencies is insufficient to supply a large h nu quantum. This causes the radiation intensity to drop, preventing the ultraviolet catastrophe and hinting at nature's granular fundamental level. In 1905, Einstein proposed that light itself is quantized into discrete energy packets called photons, with energy E equals h nu. This led to a bold, testable prediction. In the photoelectric effect, the kinetic energy of emitted electrons should depend on the light's frequency, not its intensity. This demonstrated light behaving as both a wave and a stream of particles. Experiments on the photoelectric effect confirmed Einstein's prediction. They revealed a threshold frequency below which no electrons are emitted. Light intensity affects the electron count, not their maximum kinetic energy, which depends linearly on frequency. This photon model explained why classical wave theory failed, as a single photon must carry enough energy to overcome the metal's work function. Einstein's photoelectric equation, HF equals phi plus 1/2 mv squared underscore max, is an elegant expression of energy conservation. It shows the photon's energy, HF, equals the energy to escape the metal phi plus the leftover kinetic energy. The equation's predictions, including the threshold frequency and the linear relationship between kinetic energy and frequency with slope h, were experimentally confirmed. Louis de Broglie proposed a symmetry. Matter particles can behave as waves. The de Broglie hypothesis states that every particle with momentum p has an associated wavelength lambda equals h/p. For small electrons, this wavelength is comparable to atomic spacings, making wave behavior observable, as experimentally confirmed by Davison and Germer's electron diffraction experiment. The profound principle of wave-particle duality states that radiation and matter both exhibit wave and particle behavior. Interference and diffraction show wave nature, while the photoelectric effect and quantized energy exchange show particle nature. These two descriptions are complementary and necessary, forming the very essence of quantum physics.